Today we will talk about binary search tree. Basically, it's another data structure to store data. And besides what we usually see like vector, matrix, or data frame. And this is the structure, a tree structure that we are going to create today. And it also has the property that it's the value at the left child will be less than your parent node, and your right child will be greater than your parent value. And this is the basic structure with the property that we are going to define today, which is called a binary search tree. And this R6 is the reference class that we are going to use today. R also have many different classes, but this is the one that we're going to use in this example. So yeah, make sure you load this R6 class, and the node is the first class that we want to create here. It needs a class name, and preferably the same as what you define your class. And yeah, so basically we are listing things here, so we need a comma here and a public as well. And this is a list object. Again, it's a list of the component that we need. And for a node, we will have a current value, a left value, and a right value. So here we are going to do lots of things for initialization. Yeah, make sure that you use a equal sign here, not the right arrow, because we are inside the list. We are listing all the elements, and inside the function you are able to do that. You are able to use the right arrow. Yeah, again, here we are doing lots of initialization, so it might sound a little bit, it might look a little bit tedious or repetitive at this moment. Yeah, and this is inside the function, so we can use the right arrow here. So we're going to let the val equal to whatever we assign to this node, and the left is just left, right is just right. Yeah, so yeah, like I said, we are doing lots of initialization, so lots of copy and paste. So defining 3 elements for a node and then initializing. So if we call the initialize this node, we're also going to store the corresponding value to there. And default is all going to be null as well. This is a node class, and we need another binary tree. For now, R6 as well. Okay. Class name and itself. So it's going to be a BST class and a public. It's a list. This time a tree, so we only need a root, and it will be null as well. Now we are going to define a insert function. So we are going to insert a particular data value to this tree. So if the self, so this is talking about the root of a self is referring to BST. So when you initialize this or create an object of this class, then you can always call self, and talking about this object. So we want to check if the root is null or not. If it is null, then at this root, we want to create a new node, and we initialize new node by calling a new function here, and then call data. And this data will be the value that we store at the parent value. So if this tree does not exist, at the root level, define a node. This node will have a node no left child and a node right child, and the value will be the one that we assign here or here by calling the insert. Else self dot insert recur. So this is another function. We haven't defined it yet, but we'll do it later. But now we just call the function here. It need the data value. So if 3 as a node as a root exists already, then say if the data equal to 2, then we want to check if we should go to the right or left, and then make sure we store this 2 at the correct position. So we also need another argument here, and this one for the first time we call the insert, we check about the root, but in the second time we will need a current node, and it will make sense when we define this function here. So yeah, so now we're going to define this function here, and it's going to be a function. Make sure you have an equal sign and the comma here, because we're inside the list. We're listing lots of things here, so don't miss the comma and equal sign for the comma for the function. But inside you can use the right arrow, the left arrow. So like what we have here, it needs a data and a current node. So at this part, when we call this function, the current node will be the root. But as you can tell by the name, it's a recursive function. So we at each time we call it, we need a correct position for to insert the data. So now we need to check if it's dot no and then current node at the left. So we don't need to check if the current node is empty or not, because this is already taken care at the first time you call the insert. At the second level, when you call insert recur, for sure the root will going to be a node, but you need to check if the left child of the root will be empty or not, will be null or not. So we'll need to do something here. Else if is done null and current actually no, yeah, sorry about that. First we need to check if the value is greater or less than the value, so this should be val. So what we do is that if the data, so at the self.root or the current node is not empty, then we need to check if the data is less than the current value, and if the data is greater than the current value. And then, so this will move to the left node, this is mean we'll move to the right node, and then else is that if they are equal. So we print value already in tree, and we do nothing. And we need to do something in the two cases here. So now we need to check if no current node dot left. Okay. So now if the left is empty, so the left child of the current node if empty, then current node at the left position call the new node with data value. Same thing as what we did at the root position. So if the left child of the root or the left child of the current node is empty, define again. Else, if it is not empty, don't forget to call the self. Insert recur and data, and then we want to insert that data at the current node at the left child. So we call itself again, the one that we are creating right now, we call itself again. Don't forget, if you call the function, you need to do the self $, because this is inside this self object here. And we want to input this data and then check the current node, the left child. So that means if 3 is not empty, we insert the 2, and then we check the next level. If the 2 is also, or if this position is also not empty, we check the next one. So we need to keep going down by calling the recursive function and then we need to check the left child as well. Same thing here, we can just copy paste, and we need to check if the right, and then if right is no, create a new node at the right child, and then if right is also occupied, then keep going down at the right, because your data is greater than your current value, so keep going down. So make sure you pause this part, and then make sure you understand, or if this makes sense to you. So we check if the date, so yeah, from the very beginning, if the root is empty, create new node. If the root is not empty, go down one level, yeah, and then call the recursive. So check the data. If it is, so if it should go left to the left child, and then we need to check if the left child is empty or not, and then same thing here. If we decide to go right, and then check if the right is empty or not, or keep going down to one level. So you can also go down right, but the value is no longer greater than the current node, and then it probably less, so you go right and then go left. So this is how it can achieve by calling the recursive, until you meet the condition, and then until you meet the condition for the leaf node, and then you adding. So pause the video and make sure if it makes sense to you. So with this, with insert and insert recursive, then we should be able to build a tree. And one last exercise here, in this particular example, I will just talk about get the height. We only need a current node. Yeah, so if you think about the tree, your height of the tree will be the maximum of a subtree. So this part, for example, is a height of 2, height of 3, so your tree should be height of 3. And at your second part, your height of 1 and a height of 2. So at this node, you should observe a height of 2. And yeah, so here we first let's get a sketch. Don't forget to call the self and get height. And then, like I said, is height will be the maximum of your left or right. So we'll have something like this. But what about the leaf node? If we achieve a leaf node and it is tempting to current node dot val, if it is empty, if it is null, then we will return something, and then else. If it is not leaf node, then we will return the maximum of your left or right child. Yeah. So now back to the question, what about the leaf node? It's tempting to return a 0, but when, for example, if you're so if you go down one level, so your left and right will still be null, it will return a 0. And this part, your left is also null, so it will return a 0. But here, you will also going to return the maximum of a 0 and a 0 will return a 0. So if you keep doing that, when you go back all the way up to the root, it will going to be a 0. So what we want is that whenever you return to your parent, you want to plus a 1. So you want to have a max of your left and right, but plus 1. And in this case, your root, then that means at your root, you shouldn't return a 0 as well. And because yeah, if you think about that, if you want to populate or return a plus 1 all the way back, then at the leaf node, you only have one option, is that you can only return a minus 1. So that when you add this part, you return a minus 1, but it will add a 1, plus a 1 because of the max, because of the second condition, so it will cancel out. So it will return a 0. But when you're up to your parent level, node, now you will return a +1 and then a +1 and +1. So the +1 would take care of you keep going up besides returning a 0. But only at the leaf node you need to return a -1. So to compensate the +1 at this gap, or the one level up. So make sure, feel free to pause here and then to see if it makes sense to you. So this -1 here is to take care of the leaf node, and this +1 here is to take care of the when you keep going up and then you want to get a parent node. So the height of your parent. With that, we are ready for checking. So call the reference class, your node, and your BST class. Once you load it, so you will have these. And let's create a BST binary search tree by calling the new here. This is the class and call the new. You create an empty tree. We insert as what we in this example here. So 3, 2. Okay, we have some error. In the insert recur. So if argument, so that means my current okay, so insert recur and then at the self root, and then if the data is less than that. Okay, so it seems like this part is wrong. That means this part is not getting the so the data, if the root is empty, create a new node. Let's check if okay, so that means my node function probably has something in this part. We need to call the self because we are creating node. We are storing the self value. So yeah, creating a class can be very complicated, so it required very attention to detail. So whenever you call or you store value to itself, to this node class or to the class inside this object, then you need to call the self. So I probably will miss some of the self here, so let's see if we have other error later. Okay, whenever you change your class, you should always your definition of the class, you should always call the class, reinitialize all the class elements. So make sure you need to rerun everything once you change. And yeah, okay, it ran properly. And yeah, so first let's check the root. It returned a 3. So yeah, if you want, you can go through this get height function and then to check each time when you call it. So this is also a recursive function. You call yourself again. So you can try to see when you call here, we call a root. And then you can try if you input a root and then what will happen, and then using this as an example and see if you can follow the logic or what I was go over earlier. So the -1 and +1 thing. Yeah, so our get height function is correctly specified. It will return a 3, so it will get this. So at the end, it will be a max of 2 and 3. It will return here. And yeah, we also specify the tree here. And let's check. So let's start from the BST root. We'll have a 3. Yeah, so this is the default print function. So if you think this is ugly or if it's not what you want, you can also rewrite a print function override this. But I will just use this. It will provide the necessary information that we need here. So you can what I was trying to say is that you can rewrite that to override this part. Okay, but yeah. So at the root we have a 3. This is what we have here. Our left and right are also going to be 2 node classes, and in R6, yeah, so it will be 2 nodes. And the root, the left of the root, so it's a 2. And yeah, here we have a node for the right child. So is that what we want? And yes. So our left will going to be a node class, but our right will be a node. So if we don't specify, from our definition, the right child will be a node. What about the right child? It will be 5. So we're not still talking about the right of a root. So this is 3, 2, and 5. What about the left child of the left child from the root? It should give you a 1. And there's nothing under 1, so still be no. And nothing under 2. Nothing under, this is the right, the left of the right. So 4, yeah, so it should be a 4, but nothing under 4, so it will still be no. And we are here, and it will be a 6. And 6, nothing on the left. So yeah, nothing on the left, and there's one more for the right node. So this will be the last one. And all the things here, it will still be no, no, and until the last one, it will be 7. And then only, yeah, so under that, there's nothing, so it will still be no. So as you can see, yeah, with this class, reference class here, with a node and a binary search tree class, we are able to create a data structure like this. And this is a tree structure that we can search, that we can store data. And later on, we will talk about how we can extract or to trim the tree, say insert, delete, and add another subtree inside under a particular value, and then to extract different values. So there are lots of things we can do in this particular data structure. So we usually work as using matrix or vector. A binary tree is also a important data structure. And this is just a basic creating the tree and also using the reference class. But there are, and later on we will talk about more on how we can use this kind of a data structure, and also related to this reference class. And thank you very much.